Good day, everyone. In this lecture, we'll be considering signal manipulation and waveform representation. And to begin, we're going to be considering addition, multiplication, subtraction, operations, and also amplitude and time scaling, reversal, and shifting of signals. And then we'll go on to covering the mathematical representation of signal waveforms using step and ramp functions. So let us begin. So let's consider two signals, say S of t, x1 of t. So here we want to perform addition, subtraction, and multiplication on the following signals, okay? So let us assume we have a signal S1 of t described as such. So let's assume this is -2, -1, +1, 2 is the origin. This is x1 of t and this is t. Here we have amplitude 2, +1 here, and -1 here. And then we are given S2 of t, says something like this. So let's say these are just rough sketches. Let's say this is 2. This is 2. Then, so let's assume this is -2, -1, 0. Let's assume this is 1, this is 2 in the time scale. Then this is S2 of t. So let's assume this is 4. Then this is 2. This is -1. So to perform addition, subtraction, and multiplication on these signals, let us draft a table summary. Say t, now we have -2, -1, 0, 1, 2. Okay, so we have. Then we have x1 of t. Then we have S2 of t. Then we have our addition, subtraction, then our multiplication. Okay, so let's millimeter on this. So at t-2 for S1 of t, the amplitude is 1. This point. Then t-1, the amplitude is 2. Then at t equal to 0, the amplitude is also 2. And at t equal to 1, the amplitude drops to -1. Then at t equal to 2, the amplitude is 0. Then for S2 of t, at t equal to minus 2, here the amplitude is minus 1. Then at t equal to minus 1, the amplitude is 2. T equal to 0, amplitude dropped to 0. Then at t equal to 1, amplitude increased to 4. Then at t equal to 2, the amplitude drops to 0. So in addition, this plus this, that's plus 1 minus 1 is 0. 2 plus 2 is 4. 2 plus 0 is 2. Minus 1 plus 4 is 3. And then this is 0. Then this minus this, that's 1 minus minus 1, that's 1 plus 1, that's 2. 2 minus 2 is 0. 2 minus 0 is 2. Minus 1 minus 4 is minus 5. 0 minus 0 is 0. Then 1 times minus 1 is minus 1. 2 times 2 is 4. 2 times 0 is 0. Minus 1 times 4 is minus 4. And 0 times 0 is 0. So let us pull out the three scales. First for addition, that's 0 here. This is minus 1, minus 2. This is 1. This is 2. This is the time axis. So as the maximum value here, we have 4. Okay, so let's assume this is 4. Then let's assume this is 3. So let's assume this is 2. Let's assume this is 3. Let's assume this is 2. Okay, so this definitely will be 1, right? Okay. So it's all positive values. So I'm going to use this scale for x1 of t plus s2 of t. So let's pull out the second scale. So here we have up to minus 5. Okay, so let's assume this is negative 5. And then we have positive 2. So let's say this is positive 2. So in this scale, we have minus 1. Oh, sorry. We have positive. That's a positive scale. Okay. Yeah. So this is positive 1. And this is positive 2. This is negative 1. This is the origin. So this is negative 1. And then this is negative 2. So we're going to be using this to perform the subtraction operation. Then the final graph. So this is t. So we have negative 4. So this is negative 4. Let's say this is negative 4. Let's say this is positive 4. Okay. Let's say this is positive 1 here. Then let's say this is negative 1 here. Okay. Negative 1. This is 0. So this is negative 1. So this is negative 2. So this is positive 1. So this is positive 2. So this is time axis. So we're going to be performing the multiplication operation here, S2 of t. Okay. Now, if we add these two signals together, then the signal waveform will be as we have in summary here. So at t being the same as -2, then here the signal amplitude is 0. So we have something like this at this point to 0. Okay. Then at t equal to -1, then the amplitude rises to 4. So 1 plus something here. So that's 2. Okay. Then goes all. So at t equal to 0, the signal amplitude drops to 2. Then progresses. T equal to 1, the signal value increases to 0.3, amplitude of 3. Now t equal to 4, to 2 rather, drops to 0. So the addition operation of x1 of t and x2 of t will give us this as the output. And for the subtraction operation, at t equal to -2, the amplitude is 2. So we have something here. Then at t equal to -1, so the amplitude drops to 0. Then at t equal to 0, the amplitude rises to 2. So say here. So t equal to 1, the amplitude value comes to -5. So it comes this way. Then at t equal to 2, then it comes back to 0. So that's what we get. And for the multiplication operation, at t equal to -2, we have -1. So -1 is somewhere here. Then at t equal to -1, then we have 4. So 4 is somewhere here. Okay. Then at t equal to 0, then we have 0 here. So then at t equal to that's 0, 1 here, then t is the same as -4. So we have this plot here. So signal is going to come this way, then go this way. Then at t equal to 2, then the signal comes back to 0. So when we multiply x1 of t and x2 of t, this is what we get. Okay. And let us see another operation. Time scaling. I will say in time scaling, the time scale here, the time scale is multiplied by some parameter beta, where beta is the same as 1 over p, to achieve one of two things. Okay. So the first is signal compression. Where say S of t in the input is fed into a system, beta, for which beta is the same as 1 over p. Then we're expected to get an output, y of t, which is the same as x. Since it's time scaling, the scaling parameter has impact only on the time scale. So that will be beta times t, which is the same as x of p, that's t, for beta being the same as 1 over p. And in this case, for all values of p greater than 1. Okay? And the second thing we wish to achieve with time scaling, or we could achieve with time scaling, is signal expansion. Okay? So in this case, S of t is fed into the system with the scaling parameter beta being the same as 1 over p. And then we have y of t being the same as S of beta t, which is the same as x over t over p for all p less than 1. So at this point, we should know that the parameter beta operates only on the time scale, like I said earlier. So it does not have any impact on the amplitude scale. So let us perform an operation on a few signals. So let us perform time scaling on a given signal, say S of t given the above signal. This is -2, this is +2 amplitude, -2 amplitude, and the time scale here is +2, and this -2 SNT. So first, let us perform signal compression. So in this case, the signal is fed into some system where P, say P, is equal to 2. And recall that we have y of t to be the same as x of t over p. So in other words, we're going to be having x of t over 2. Okay? So how will the output look? So let's check on how the output will look. Okay. Let's use the block for the scale. So in this case, we have 1, 2. So this is compression. 1, 2. So this is -1, it's -2. This is +1, and this is +2. It's a time scale. Now, this operation have no impact on the amplitude of the signal. So we have +2 here, and then we have -2 here. So this time, this case, we have y of t. So at t equal to -2, at t equal to -2, then what we have here is s of t over 2, which is minus 2 over 2, which is the same as s of minus 1. So meaning, right here, looking at the input, at t equal to minus 2, the amplitude is minus 2. So subsequently, at the output, we have the same amplitude of negative 2 at t equal to minus 1. So we're going to get something like this. And then at t equal to 0 as the origin, equal to 0. So we have x of t over 2, that is 0 over 2, which is x of 0. And for s of t is positive 2 at t equal to 0. Now, on performing the time scaling operation, s of y of t will be 2 at t equal to 0 as well. So we're going to get our signal here. Okay, so we'll trace this all the way. Now, t equal to positive 2, then s of positive 2 divided by p, which is 2, will give us s of positive 1. So hence, positive 1, the signal drops to 0. So you can see this is a compressed version of the input signal. Okay. Now, let us use the same signal waveform to perform signal compression. So let's get this out. So for signal expansion, say P is the same as 1 over 2. So it must be less than 1. So here, we're going to get S of t divided by 1 over 2, which is S of 2t. Okay. And then the output will look something like this. This is now y of t. So we have 1 here. Let us see, we have 2 here. Then we have positive 4 here. We have, let's make it look similar. This is 2. This is 4. This is 2. This is 4. Okay. So this is amplitude of 2. It's another amplitude of 2. So here we have minus 2. Here we have positive 2. So this 0. This minus 2. This is minus 4. This is positive 2. This is positive 4. And this is t. So at t, because here we have s of t at the input and At the output, we have y of t to be the same as s of 2t. So at t equal to -2, then y of t will be the same as s of 2 times -2, which will be s of -4. Okay, so meaning at s of -4, we have the amplitude of 2. Okay, then at t equal to 0, t equal to 0, s of t is 2. Then y of t will be the same as s of 2 times 0, which is equal to 0. So it means here, t equal to 0, we have s of t equal to +2. Okay. Then at t here, equal to +2. Then y of t is the same as s of 2 times +2, which is equal to +4. So it means yes. So you can see this is an expanded version of the input signal. Hence, in order to perform compression and expansion on signals, what we need to do is to perform time scaling. Okay. Now let us look at a special case of time scaling, which is time reversal. So let's make the fifth one. Time reversal. So in this case, we say this is a special case of time scaling, where the parameter beta is equal to -1, such that beta equal to 1 over p is still the same as -1. So if we consider the original input we used, that is -2, +2, +2, this is 0, this is -2. S of t, this t. If we feed this into an input, where beta is the same as -1, -1, then the output is going to look something like this. So we have -2, we have +2, we have -2, then we have +2, this is 0. So in this case, this is the output y of t, okay? Because here we have s of t at the input, so it goes through the system. So we have y of t being the same as beta s, same thing as s of beta t, for which beta is -1, so -t. So it means s of t same as -t. So at t equal to -2, then y R of t is the same as S of minus times minus 2, which is equal to positive 2, right? S of positive 2. So it means where the amplitude is negative 2, right? So now it is now positive 2, right? Yeah, so the amplitude goes something like this. So at t equal to 0, then we have S of minus 0, which is approximately the same as S of 0. And then the value sorry, something wrong here. Here, this is the amplitude. Okay, it's at minus 2 amplitude. We had this reversal, so it became positive. Yeah, so that at 0 it is still positive 2. So the signal comes up this way. Okay, so meaning at t equal to minus 2, then we have the time reversal here. So minus times minus 2, that's positive 2. So it means that on the time scale, it is positive 2, but the amplitude is still negative 2. Okay, then at t equal to 0, that's S of minus 0 is the same as S of 0 approximately. Okay, then at t equal to 0, the amplitude is positive 2. That's what we get here. So at t equal to positive 2 at the input, and at the output, we have S of minus t will be the same as S of minus 2. So it means that the time scale is going to be S of minus 2. And at S of t equal to positive 2 at the input, the amplitude value is 0. So here it returns to 0. Now you see that this is a reflection of the input. So we call it folding operation as well, such that the signal is seen to is seen as a mirror reflection of the input. So the folding is about the amplitude scale. Okay. Okay. Let's look at amplitude scaling. Now, in amplitude scaling, the amplitude is multiplied by some parameter beta to achieve one of two things. Now, the first of which is signal amplification. And the second is signal attenuation. Now, to achieve signal amplification, assume we have an input S of t into a system beta characterized by some parameter beta, then y of t will be the same as beta S of t. So in other words, the amplitude scale is multiplied by the parameter. For all values of beta greater than 1. And for signal at attenuation, so f of t is fed into a system characterized by some parameter beta, and there we have y of t being the same as beta times s of t for all values of beta less than 1. Okay. So let us consider the original signal we also used. So this is -2, this is +2, this is +2, this is -2, this is 0. So this is S of t, our input. And then this is the time scale. So if we feed this through a system, say beta is the same as 2. So here, this is greater than 1. So we should expect amplification. Since beta is greater than 1. So this is going to give us something like this. Excuse me, please. Now, here, the amplitude parameter is multiplied. Okay? So at t equal to -2, here, now the amplitude value is -2. So we have the amplitude value multiplied by the beta parameter, plus here, y of t is the same as beta s of t. So beta is 2 times the amplitude -2, which is equal to -4. So you see that the amplitude, if this is -2, this is -4. So you see the amplitude rises for the same time scale. So the amplitude is amplified. Then at t equal to 0, here, the amplitude is +2. So that will be +2 times 2. That's the beta 2 times the amplitude +2. So that's going to give us +4. So it rises all the way. This is y of t to some value, which is 4. Okay. And then at t equal to +2, as at this point, the amplitude value is 0. So we have 2 times 0, that's the beta parameter, which is equal to 0. So it means at +2, the signal waveform returns to 0. So you see this is an amplified version of the signal. Now, in the case of signal attenuation, suppose we have the same signal, S of t, that's -2, is +2, is +2 amplitude, -2 amplitude, 0 is time scale S of t. Then we feed this into a system where beta is the same as half, because for attenuation, beta is less than 1. Then we have our output. Now, given that this is S of t and this is y of t, and y of t is the same as beta s of t, and then this is the same as 1 over 2 s of t. So at t equal to -2, the amplitude is -2. So y of t here will be 1 over 2 times -2. So that will give us -1. So if this is -1, then this is 2, this is -2. Then at -2, the amplitude value is attenuated. Okay, now at t being the same as 0, the amplitude is +2. And there y of t is the same as 1 over 2 times 2, which is equal to +1. So this is +1, and this is +2. Then this is what we get. Okay. And then at t equal to +2, then y of t is the same as half times the amplitude value here is 0, equal to 0. So means that at +2, the amplitude value returns to 0. So you can see this is an attenuated version of the input signal. Okay, so just like in time scaling, the beta parameter in amplitude scaling has no impact on the time scale. It only has impact on the amplitude parameter. And now let us look at another operation on signals, that is amplitude reversal. And this is a special case of amplitude scaling. Where beta is the same as -1. So given the same input as used previously, then this is -2, this is +2, this is 0, this s of t, this t, fed into a system where beta is -1. Then if this is s of t, this is y of t, then it means that y of t is the same as beta s of t, which is the same as -1 times s of t minus s of t. Okay, and so what do we get at the output? So it means that at t equal to -2, and this is +2 amplitude, -2 amplitude. So it means that y of t is the same as negative times -2, which is equal to +2. So it means that at -2, the amplitude is +2. Okay, let's use, so it doesn't look like, okay, I know, just reversing the amplitude. So let's use scale that is comparable. This is -2. Okay. So this -2, and this is +2. Okay. Then now at -2, at the input we have +2. amplitude. So let's do this positive 2, for instance. Positive 2. So here's something like this. So at t equal to 0, t equal to 0, then the amplitude becomes positive 2. So y of t is the same as minus 1, which is beta, times positive 2, which is minus 2. So at 0, then this becomes negative 2. So we can have the signal all the way to negative 2. And then at t equal to positive 2, y of t is the same as negative times 0, because at t equal to negative 2, the amplitude reduces to 0, which is approximately equal to 0. So then we have the signal come like this. So you can see here, this is y of t, this is t. The signal is seen to have folded about the time axis or the time scale. Okay. Okay. Let's look at time shifting. Now, in the case of time shifting, this is the movement. This is the movement of a signal to the right or to the left on the time scale. Okay. So in other words, a parameter, say alpha, is added to the time scale. That is the time scale to achieve one of two things. One of two things. Okay, and before we do that, which is time advance and time delay. So let us see what this really means schematically, using a schematic rather. So we have S of t getting into a system characterized by some parameter alpha, which is expected to perform time shifting. Then y of t, here we say that y of t is such that the signal adds that parameter to the time scale. Okay. Now, do take note that we said that this parameter alpha is designed to achieve one of two things, and the first of which is signal advance. Okay. Or better still, left shifting. And for this to happen, alpha must be positive. A positive value. Okay, positive value. Okay, so it means S of t goes into a system where alpha is positive, that is positive alpha. positive alpha. So we have of t to be the same as s of t. Since it's positive plus times plus is positive still, alpha. Okay. In case of signal delay, or let us say right shifting, this will be very relevant when we come to waveform representation. Here, alpha is negative value. Then it means that s of t goes into a system where alpha is negative. And then we have y of t being the same as s of t minus alpha. Because minus times plus, minus and alpha. Okay. Let us consider something. Time shifting. Okay. Now let us assume we have the same signal we used previously. This is -2. This is +2. The amplitude here is +2, while the amplitude here is -2. There's 0. This is s of t. And here we have time parameter. So let's assume we want to perform signal advance, or better still, leg shifting. So from our definition, alpha has to be positive value. Okay, so let's assume we have positive value 1. Okay, just a positive value 1. So then we have this output y of t being the same as s of t plus 1, right? Plus alpha, because y of t is the same as s of t plus alpha. And alpha is +1. So we get that. Okay. Now, what's going on? How would the output look? So let us draw this out. Now we have time scale. Let us grade it properly. 1, 2, 3, on and on. 1, 2, 3, on and on. So in other words, this origin 0. So we have 1. We have 1, 2, 3. Right here we have -1 here. This is -1. This -2, -3. Okay. And then we have amplitude. Since it's time shifting, it has an impact on the amplitude value. So let's say this is our amplitude of 2 here. 2. And this is our amplitude of -2. It's -2, 0. Okay, let us begin. So in other words, we have s of t getting to the system. Then we have our output y of t being the same as s of t plus 1. So technically, our t at the input is equivalent to our t plus 1 at the output. So this is input, this is output. Okay. So I think now we can begin our analysis. So at t equal to -1, -2 rather. That's at t equal to -2 here. That's t equal to -2. The amplitude value is -2. But here, following this relationship, then it means that 2 minus 2, which is t, is the same as t plus 1 at the output. So t at the output will be the same as -2 minus 1 equal to t, which is equal to -3. Okay? So it means that at the output, the signal shifts to the left, and then we have -3, right? Good. Then at t equal to 0, then t having a relationship of t, the input, and t plus 1 at the output, called t here at the input is 0, same as t plus 1. So 0 minus 1 is equal to t, so t is equal to -1. So it means that t equal to 0, the amplitude is +2 at the input. So at the output, the amplitude is +2 at t equal to -1. This is 1 minus 1. See that? This is what we get. Okay. Then at t equal to +2, so we have the relationship t at the input and t plus 1 at the output. That's 2, being the same as t plus 1. So 2 crosses this, plus -1 equal to t. So that will be t equal to 1. So at t equal to -2, the amplitude value is 0. So at the input, so at the output, at t equal to, the amplitude is 0 at t equal to -1. And here you see that the signal has shifted. Signal has shifted to the left. Now, well, this gives us some, well, there's a level of concern anyway, because is this really realizable in practical systems? If yes, what kind of systems? And if no, why? Okay, then let's begin with the yes. Or let's begin with the no. In practical systems or real-time, or let's say practical or real-time systems, we experience delay in the signal. Say I transmit at time t equal to, say, 1 o'clock. I should receive my signal at a later time. Let's say this is 1 p.m. I say 1.12 p.m. Okay. Now, if I transmit at 1 p.m., I should not receive the signal at probably, let's say, 12 p.m. of the same day. It's an earlier time. and this is a later time. So time advance is actually saying that we receive the signal earlier than we transmitted it, because the signal is shifting to the left. This is an earlier time. This is a later time. We can say this is the future here. And here, this is the past. Okay? Now, if this is the future, we should receive our signal in the future if we transmit in the past, or if we transmit right now. But when we deal with storage systems, we can actually liken the system to be operating in using the time advance operation, for instance. Now, example of such systems are database systems and even biometric systems. Let's assume you want to perform facial recognition. So some samples must have been stored up in the database. And at the point of authentication, it goes back to the output. Now, the output is to authenticate with the face of, say, Mr. X. Now, should Mr. S show up, the system will have to go back to the database to compare the identity of Mr. X with probably the image that was stored up in the database previously. So in other words, we have knowledge of the output. So should we design a system where we already have knowledge of the output, then we'll say that is time advance. But in real-time systems, what we experience is time delay. So let us look at an example of time delay. Okay. So let us assume for time scaling, what is time delay. So let us assume we have the same signal waveform. This T, this is S of T, this is +2, this is -2, this is 0, this is -2 amplitude, +2 amplitude, okay? So we feed this to a system where alpha is negative. And then we have y of t being the same as s of t plus alpha, which is now the same as s of t minus 1, plus alpha is -1, okay? How should the output look? Now, here, the input s of t is related by s of t equal to s of t minus 1. So in other words, t is the same as t minus 1. So at the input, we have t, and at the output, we have t minus 1. So when t at the input is the same as -2, that's -2, then we have t minus 1, so -2, then minus crosses the equality sign, that will be +1 for the t, so that's -1. T is the same as -1. So in this case, we have minus -1, -2, okay, there's 0. So meaning the amplitude of -2 comes up to -1. Okay. Then, how about t? At t equal to 0, then we have 0 turning to t minus 1. So 0 plus 1 is equal to t. So t is equal to +1. So here, this is 0. So let's say this is, that's +1. And then this here should be +2. So it means we have the signal coming here all the way to 2, because at t equal to 0, the amplitude is +2. So here we have +2, right? Then at t equal to +2, so we have t turning to t minus 1. So that's +2 is the same as t minus 1. So that'll be 2 plus 1, which is equal to t. So t is equal to +3. So it means we now have to, let's create the scale properly. That's 2. And then this is +3. This is +2. So it comes to 0. So now you can see that this is y of t, this is s of t. So the signal was shifted or has shifted to the right. Okay. And then we say this is time delay. Now, why is it time delay? Okay. So if this is the present time, because this is an earlier time on the scale, coming from -infinity to +infinity. So if this is the present time, then this must be the future time. So you can see that the signal has moved from an earlier time into a future time. So it must have taken some time for this signal to travel from its original state to the present state, because the original signal looks something like this. You can see there is some time in the future the signal is appearing. So in other words, it took some time, which is the delay for the signal to appear in the future. And you see that in practical systems, what we experience is time delay. Take, for instance, mobile communication. Once your signal is transmitted, either through your mobile device or through your telephone device, it takes some time to go through the entire network process and then rings at the other end. So the time it takes for you to initiate the call and then for the call to be paged is delayed. Okay, it takes some time. And we now see that even in your printing / scanning device, once you initiate the printer to print a document, it takes some time to initialize. Then afterwards, the system responds and print your document. So you don't get it instantaneously. There's a time lag. So When we model practical systems mathematically, we're going to be seeing some negative sign on the time scale to show that it is actually, or the signal is actually experiencing some kind of delay. Okay, before we go into waveform analysis or representation, let us consider amplitude shifting. Amplitude shifting. So we'll run through this quickly. So this is the movement of the signal upward or downward. So in other words, we add a parameter, a DC component, to the signal. Okay, so let's assume we have S of t, feed it through a system. And then we have a parameter alpha. We are saying that y of t will now be the same as S of t plus alpha, where alpha is a direct current value, or it's a DC, or it's a real number. Okay, it's an absolute value, say 1, 2, so on. Okay, so in other words, the signal on the amplitude time scale, the signal can either move upward or downward. So let's take our original signal for instance. So this is -2, this is +2, this is 2, this is -2, this is 0. Time scale S of t. So if for instance we have alpha to be, say, positive, say it's positive, let's say +2. Okay, this is S of t, then y of t will be the same as S of t plus 2. Okay, so in other words, we're going to add 2 to the amplitude. So at t equal to -2, here the amplitude is -2. So if the amplitude is at t equal to -2, the amplitude is equal to -2. So here we're going to add it to this S of t plus 2, which is equal to 0. So it means that t equal to -2, the amplitude from 0. Let's use amplitude is 0. Okay. Then at t equal to 0, the amplitude S of t is the same as +2. And we're adding 2 to it, plus 2 is equal to 4. So if this is 2, then this is 4, right? So the signal goes up this way. And then at t equal to +2, the amplitude is 0. S of t is equal to 0. Then we add up 2 to it. So y of t is equal to 2. So this is 2 here. Then we get this, and this comes out this way. So this is what we get. We can see it went upward. Now, what happens if, for instance, the parameter is negative, so let's assume alpha is equal to -2, right? So here, we're going to get something like this. Now, at t equal to -2, the amplitude s of t is equal to -2. So y of t will be -2, which is s of t plus 2. But this time, it's not +2, it's -2 because alpha is -2, right? -2, it should be -4. So it means the amplitude, we have 2 here, and we have 4 here. So at t equal to -2, so what you get is this. Then at t equal to 0, s of t is equal to 2, such that y of t is the same as 2 minus 2, which is equal to 0. So it means this goes to 0. And this is positive 2 equals to 0. Right? Amplitude is 0. Then at t equal to positive 2, then s of t is equal to 0. That's s of t is equal to 0. Okay? And then y of t will be the same as 0 minus 2, which is equal to -2. So this is -2 here, this -4. So the signal comes to, I can see the signal moves downward when the scaling parameter is negative. Okay, so let us go to the last session for this class or this tutorial, which is waveform representation. Now, conventionally, signal waveforms can be represented by either ramp or and step functions, okay? So we'll just take a quick review on step and ramp function. So when we say unit step function, now, or better still, Heaviside function, it is defined as u of t such that the value is 1 for t greater than 0, and it is 0 otherwise. That's for t less than 0. Then we have the waveform, looking something like this. U of t is time t. So since it's a unit step function, so the amplitude is 1, then that's what we get. And then is 0 at negative infinity to 0. And at this point, call this point the point of discontinuity, because the value at this point is undefined. Now, why that? You see that at this point, point 0, parameter would either be 0 or 1, because the value keeps increasing gradually. And as such, since the value is undefined, at this point, we call this point the point of discontinuities or discontinuity. Okay. And the second is the unit ramp function. Unit ramp function R of t, and it is defined as having a value of 1 for t greater than 0 and 0 for t less than 0. Yeah, greater or equal to 0. T, yeah, it's called a t rather, not unit step is 1, ramp is t. And there we have something like this. It's about 45 degrees. This is t. This is r of t. And here, meaning the gradient will definitely be 1 this time, 45 degrees, okay? So, it should be noted that the ramp function and the unit step function are related by, say, r of t is the same as the integration of u of t dt. Okay? So how is that? So let us prove this. If that's what it is, we have u of t to take on values from negative infinity to t, okay? Some value t, such that between negative infinity to 0, u of t is 0, 0 dt, plus from 0 to t, limit t, then u of t is 1 dt. And this is the same as 0 plus t, for which t takes on values from 0 to t, which is the same as t. Now, since u of t is the same as 1, then r of t, which is the same as t, is the same as t dot 1, is the same as t u of t. So this is a very interesting relationship that we are going to be using shortly. So since we are able to integrate u of t to arrive or deduce r of t, so if we differentiate r of t, then we get u of t. Okay, then there's one more thing that is worth mentioning here. That is the unit step function. Now we just talked about time shifting, right? So what if we perform time shifting operation on, say, a unit step function? So let's assume we have a unit step function, say something like this. Here, this is 1, this is u of t, and then we want to perform time scaling, for which this is some parameter t, right? Okay, so some parameter t. Let's say t naught. Let's put it that way. Okay, some parameter t naught. So what do we get from here? So here, in order to achieve time delay, we have a negative parameter here, so such that we have u of t minus t naught, right? So the output is going to look something like this. Here, this is t naught, for instance. And t, u of t, and this is 0. And since we already figured out that r of t is the same as tu of t, hence r of t as tk delayed by some parameter tk will be the same as t minus tk times u t minus tk. So, what are the rules? The basic rules for waveform representation. Let's look at them quickly and solve an example, and then we're done. Basic rules for waveform representation. Let's see if I'll be able to squeeze it somewhere here. So the first here is that you use positive sign, use a positive sign for an upward movement or upward turn while tracing the signal waveform, okay? And then the second is to use a negative sign for a downward movement or turn while tracing the signal waveform from left to right, okay? And then the third point to consider here is that the ramp function r of t is represented as the product of the magnitude of the slope and the ramp function taking time delay into consideration, okay? And then the fourth point here is that the step function is represented as the product of the magnitude difference at the point of discontinuity and the step function. Taking time delay into consideration as well, okay? And then finally, the number of discontinuities in the signal waveform determines the number of step functions. Anyway, so okay. I wanted us to have this for easy reference here. So let's assume we want to establish the mathematical relation or relationship for a ramp function, say something like this. Okay, where at this point we have t sub 1 equal to beta, and here let's say t naught equal to 0. Then at this point, let's say we have amplitude of A. Then we have r of t, and then this is t. So here we are saying that you have to use a positive sign for an upward movement. So let us begin to trace. So we're going to trace from left to right, okay? And at this point, you see, we are tracing on t equal to 0, the t-axis, all the way, okay? So we say r of t is the same as 0. Then at t not equal to 0, there is an upward movement here. Remember, this is 0, okay? So since there is an upward movement, so we have to trace this way this time. Then all the way, we use a positive sign. Said use a positive sign for an upward turn. Okay? So afterwards, point 3 says the ramp function is represented as the product of the magnitude of the slope. So what is the slope? Now the slope is the difference between the r of t axis divided by the difference in the time axis. Okay? Times the ramp function, r of t. Now, taking the time delay into consideration. So this taking time delay into consideration, okay? We're also taking time delay into consideration. So if we take time delay into consideration, then that will be, now this upward turn was established at time t equal to 0. So that will be minus t naught. So once we plug in these parameters, so this is going to give us the difference here is a minus 0, which is a minus 0, divided by beta minus 0, that's beta minus 0, times r of t, where t naught is 0, minus 0. So this is going to give us a over beta rt. Now, since rt is the same as t u of t, then in this case, our signal, let's just call it s of t. So we could differentiate between them. So s of t, our signal s of t will now be the same as a over beta t u of t. Okay. Now let us consider another example using the step function. Let us use the step function. It's like this. Let's use the step function. So let's say we are given a step function. So something like this. This is A. And here we have the value t sub 1 is the same as beta, and t naught is the same as 0. This is t, and this is s of t. Okay. So once again, it says we should trace from left to right. So we trace from left to right. So here we have s of t is equal to 0 first. So it keeps going all the way. So it's 0. Now at t equal to 0, there is a discontinuity here. And you see that 0.5 says the number of discontinuities in the signal waveform determines the number of step functions. So here we're going to have just one step function, okay? And 0.2 says use a positive sign for an upward turn. This is an upward turn, okay? This is an upward turn. So it's positive. Okay, and it's a step function, so that brings us to 0.4. The step function is represented as the product of the magnitude difference. The magnitude here is A, that's the amplitude, okay? The product of that and the step function itself, taking time delay into consideration, okay? So the magnitude difference here is A minus 0, okay? At time t equal to 0, then at the point of this discontinuity, the amplitude difference is a and 0. So the difference is a minus 0 times the unit step function itself, u of t, considering or taking time delay into consideration. So this occurred at time t naught. So that will be minus t naught, okay? So When we substitute other parameters, so we know that S of t is the same as A, minus 0 is A, my dot, use dot please. It's a product, okay? Product times U of t, T naught is 0, minus 0. So this is the same as A U of t. It's that simple, okay? So let us look at one, example where we may have to move upward, downward, and have a ramp and a step function in it, and then I think we could call it a day. Let us consider this signal waveform. So we have something like this, and we have something like this, something like this. So let's say this is 1, let's say this is 2, this is 3, this is 4. Well, this is not to scale anyway. Pardon my funny looking graph, okay, or waveform rather. So this is S of t, so this is 0. Okay. And then at this point, let's do something a little cleaner than this. Do something like this, like this. This 1, 2, 3, 4. Then here, and here. So this is 1, this is 2, this is S of t, and then this is t, this is 0. Okay. So for us to evaluate or provide the mathematical representation of this waveform, we have S of t to be the same as, now we have to trace from left to right. So it comes in from 0. This keeps going all the way. So that is 0, right? Then at t equal to 0, we go upward. So there's an upward trace. So it says positive, right? For an upward turn, we choose positive sign. And this keeps going all the way. Okay, nothing is stopping it. Okay, and it's a ramp function. And for a ramp function, this is presented by the product of the magnitude of the slope, and the slope here is 1 minus 0, that's 1 minus 0, divided by 1 minus 0, 1 minus 0, times the ramp function, r of t, and at point t equal to 0, minus 0, taking the time delay into consideration. At this point, there's no time delay. Okay, now it keeps going. Remember, this is an angle alpha. And then we need to tilt this down. So we need to bring it down. And attempts to bring it down will be going downward, right? So we could achieve this point. Now going downward, so that this now goes this way, you will realize that then we have to use a negative sign, right? When use a negative sign for a downward turn. So that's minus, right? Negative. And now we realize that this angle is equivalent to this angle, their corresponding angle. So in other words, the magnitude at this point is the same as the magnitude at this point. So that will be 1 minus 0 divided by 1 minus 0 times, now r of t, this time, this turn occurred at this point at time t equal to 1 minus 1. Okay, all the way. And recall that step 5 says the number of discontinuities in the signal waveform determines the number of step functions. And you see that here we have just one discontinuity. This around goes all the way, then this is the first and only discontinuity here. So in drafting this equation or this mathematical model, in the first instance, we know we're going to be having just a single unit step function representation. And this is a ramp also. But now it is going upward, okay? Upward, all the way, all the way. So that is positive. And the magnitude difference between this point, between this point and this point is 1 and 2. So the magnitude difference is 2 minus 1 times the unit step function t, and this occurred at time t equal to 2 minus 2, okay? And now this just went all the way up. So we need to bring it down, right? No, came all the way. This is the step, right? Because this is discontinuity, is a step function going all the way. So this is discontinuity, and then we have the step function going all the way. And now, at this point, we have this. So meaning from 0, we had our first ramp function, which went all the way. Let us bring it down, okay? Downward turn, we had this, because these are corresponding angles, so it's the same order of magnitude for the slope. And now, at this point, we have this a single discontinuity here, and that gave us the step function. And now we have a ramp function going this way. We have a ramp function going this way. And this is going to give us a downward turn. So that will give us a negative minus. Okay. Now, in this case, the order of magnitude for the slope will be 2 minus 0. 2 minus 0, because that's what we get all the way, right? This point 2. And at this base point, this point 0. divided by. So at this point, the rotation here, the rotation is taking place at this point 2, right? This point 2. So 2 minus 0. Then times the ramp function itself, that is t, and it's taking place at this point 2, yeah, from t equal to 2. And now this goes on and on, okay, all the way. And to stop it, we'll have to tilt upward so that we have this turn. And then this angle, say beta, is the same as this angle beta. So we're going to have the same order of magnitude, but recall, it's tilting upward. So when the turn is upward, it's positive. And now we have the same order of magnitude. That will be 2 minus 0 divided by 2 minus 0 as before. Okay. And then we multiply by the ramp function r of t, and this occurred at point t equal to 4 minus 4. Okay, so the eventual signal waveform is going to be s of t equal to 1 over 1 r of t minus 1 over 1, that's this now, dot r of t minus 1 plus 2 minus 1, that is 1, dot u t minus 2 minus 1 dot rt minus 2 plus 1 dot rt minus 4. So this is going to be the same as rt minus rt minus 1 plus ut minus 2 minus rt minus 2 plus rt minus 4. And now you will agree with me that these 5 rows rather subsist. And just check this out, the 5th row. The number of discontinuities in the signal waveform determines the number of step functions. And here you can see we have just one discontinuity, which is here. This is the original signal, right? This is the original signal. And you can see we have just one discontinuity here. And we have just one unit step function. Okay. And now since u of t, or better still r of t, since r of t is the same as t, u of t, then s of t will be the same as t u of t minus t minus 1 u t minus 1, that is this, plus u of t minus 2 minus t minus 2 u t minus 2, then plus t minus 4 u t minus 4. Well, at this point, I'll say we've rounded up we've completed the design objectives for this lecture, and hope it was informative And if you have any concern, or you could leave your comments in the comment section, and hope to have you again in our next lecture. Do have a great day, and bye for now.